Moving back to instantaneous rate and average rate. So first off, what we want to do is let's calculate the instantaneous rate for the reaction at 50 seconds for both H2, the rate of disappearance, all right, and also the rate of appearance for HI. Now, the tangent lines are drawn for us here. That's important to be able to look at because tangent lines, again, are really, really difficult to draw. But at 50 seconds, right, here's time 50 seconds, we have 2 points, 1 point for HI and 1 point for H2. Now, when we are looking at the instantaneous rate, we do have to draw that tangent line. And then what we want to be able to do is construct the rate equals negative change of H2 concentration over change in time, and be able to pop in 2 points that line up with that tangent line. Notice that these are points on the actual tangent line, not on the actual curved data line, okay? And so these ones are given to us, the change of concentration and the change in time, okay? All right, so what we can actually look at for H2 is the change in concentration is a negative 0.28 according to that tangent line, and I'll put the units molarity, over the change in time, which here it spans out 40 seconds. Again, this is focusing on the tangent line itself, the purple one that I highlighted there, not the green one. And then that equals 0.0070 molarity per second. All right, so rates are always positive. That's why we have the negative in front of our rate here to make sure that the delta concentration for our reactant, which is going to be negative because they're decreasing, is normalized back to 0. All right, let's do HI. I'm going to change the color. Here's the tangent line. Again, the tangent line was constructed for us, so let's go ahead and write that rate expression. Positive, change of HI, positive because HI is a product, over 2 delta T. All right, don't forget that 1/2 is there because of the 2 in the balanced equation here. This is the same reaction that we were looking at previously. Now we're just plugging in the values. So plus 0.56 molar divided by 2 times 40 seconds. So here we're getting 0.0070 molarity per second. So they're the same. Excellent. Measuring the rate of the reaction has to be done in the lab. All right, you need to be able to measure that concentration of at least one component in the mixture at many points. Okay, so there are 2 ways of approaching this problem. The reactions that are completed in less than an hour, it is the best to do continuous monitoring, which we'll talk about next time. For reactions that happen over a very, very long time, you can actually do a sampling of the mixture at various times. Let's go and again see that same chart that we just saw, but do an average rate as if we did a continuous monitoring approach and got multiple points over our time, and then wanted to take the average over a couple different points. Okay, so looking back here again at the same equation, let's do the average rate type calculation. So continuous monitoring, I saw that this reaction took 120 seconds, right? There's 120 on time on the x-axis. So this is what a continuous monitoring type approach would look like. Now, a couple of points are located there on our curves, but we see that the curves overall look continuous in nature. So average rate, what we would again want to be able to look at is what 2 points are we going to look at? Are we going to look at the initial and final, right? And try to think about the average rate of the overall reaction, or are we going to take a couple of points in between? So let's look at the average rate here. Now let's just do the average rate for HI, all right? So let's talk about at 0 times 0, and let's stop at time 100. So from time 0 seconds to time 100 seconds. The concentration of HI at the beginning at 0 seconds is 0 molar, all right? And then HI at 100 seconds, let's just estimate that's a little bit more than 1.7, just a little bit. This is where, again, use your own scientific knowledge. Let's say 7.2 molar. And then let's construct that rate expression again. HI is a product, so plus 1/2, again, the 2 from the balanced equation goes in the denominator of our rate expression, times the delta HI concentration over delta T. All right. 1.72 minus 0, 2 times 100 seconds, right? 100 minus 0. So that 1.72 divided by 2 divided by 100 should be 0.0086 molarity per second. So there's the average rate with respect to HI over the course of the first 100 seconds. We could calculate at any interval that we chose. We could calculate with any point along this chart. This would be all looking at the average rate. Remember, the only time we care about that slope of the tangent line is when we're talking about an instantaneous rate.